Hello, Justin. You guys should not do the chatting during the lecture. I know YouTube has this feature. It's quite disturbing. Seriously, this enrichment just program is to help you to learn math better. We will spend 30 minutes on homework problems and the remaining 60 minutes on more interesting topics and just the materials that you won't learn in school or in our regular free Asian math. Because free Asian math is really trying to just give a standard curriculum and hopefully replacing the Common Core, but it does not cover much competition math or anything kind of beyond standard education. That's what we are here for. Okay, let's get started. So, this week we will continue to discuss the problem about the Gaussian summation. But before doing that, let's talk about some of the homework problems from this week. Okay. So, I believe last Friday, you have some exercises that require you to review the basic operations of vertical addition and subtraction as well. So some of the problems require you to perform some logical reasoning, and this is a problem that I found quite interesting and could be a little bit challenging for some of you. That's why we are going through this um, one more time. Although I did give you the solutions, which you should always check. So now we have this vertical addition problem. It's like a puzzle, but it does require you to exercise a lot of logical reasoning. So first, you want to read this problem carefully. So this is a vertical addition. You have two 3-digit numbers and you add them up, get a 4-digit number. But the problem says that any digit can appear in the operation at most once. So that's a pretty serious constraint because you only have 10 digits in total, right? In decimal system, we have from 0 to 9. So that's all the digits you have. But in this problem, you actually do have 10 digits. You can see that 3 plus 3 equals 4. So 3, 3, 4, that's 10 digits in total. That means that you will use all the 10 digits. And because any of them can only appear once, at most once, that means that you not only need to use all of them, and you can only use each one of them exactly once. So that's a pretty serious constraint, but at the same time, it makes the reasoning quite just easier because we only consider some special case, say any digit can only appear exactly once. So for any puzzle problem, in fact, could be non-mathematical, non-puzzle problem, could be some real life problem. Where do you want to get started? So really, we want to look at some point that is the easiest for us to get started. So we call those low-hanging fruits. If you can identify some of the easier, in this case, the box to figure out, you should always try to start at that point because once you have cracked one box, that can lead you to additional easier boxes to work out. So low-hanging fruits can lead to further low-hanging fruits. So if we look at this, what could be the very first one that you can figure out? That must be this thousands place digit, right? Because we know in addition, when you do just a place value by place value, at each point, we actually prove this in one of our exercise problems. Let's just say when you add rows to up, first without any carrying, what could be the max value you get by adding 2 digits? That must be 18 because 9 plus 9, that's the max you can get. You can never go beyond 18. And now we have to consider a potential carrying, say, from the ones place. It can be actually reasoned and proved that at any point the carrying from one digit to the next higher place value digit will be 1 at most. This can be recursively proven. Actually can also use a technique called mathematical induction, which we'll discuss later today during our real enrichment portion of the lecture. But long story short, you can actually propose and prove that each time when you have a carrying, the carrying would be at most 1. You will never have a case where you carry 2 to the next digit. As the result, when you add those 2 digits up, the maximum is at 18 and plus 1 potential carrying. The carrying could be 0, no carrying at all. If there is a carrying from the previous digit, it will be at most 1. So that means that when you consider adding 2 digits at one place value, the maximum would be at 19, right? So that further proves that when you carry to the next digit, you'll be at most 1. So at any given place, the carrying will be at most 1. That means that the local addition plus the 2 digits, you add them up, plus the carrying from the previous digit would be at most 19. So that suggests that this digit must be 1. I'm going to use a red because that's the maximum you can get. This is the most easiest, the easiest box you can solve. Then after this, we have already nailed down 4 digits. So we have 6 remaining. So it would be beneficial if we write down what rows 6 are. So we have 1, 2. So we have 0 available. 3, 5, 6, 8 is used. 7, 9. Right? So now we have to consider what's going down. After this, where should we start? Well, there's no apparent places, but we can do some reasoning because we know now there must be a carrying in this place, right? Because we have to generate this 1. That means that here, to add something needs to be fairly large. And this would be 9 because we don't know whether there's a carrying from the 10th place to the 100th place. But assuming there is 1, then the smallest number or digit you can put into this box would be 7. Because if it's 6, you will never generate the carrying 1 to the 1000th place. So we know this place can be at the most 7, 8, or 9. Considering there is a potential carrying from the 100th place. So that significantly narrowed down our choices. You can easily see among all the remaining boxes, this provides the narrowest group of just choices. Okay, so now we can do some additional reasoning based on this significantly narrowed down group of choice. So can this be 9? Well, if this is 9, assuming just this is 9, what could be this digit? We don't know whether there's a carrying from the previous digit or not, but why don't we consider both cases? If there's no carrying from the hundreds place, 9 plus 2 would be 11. That means that this box has to be 1, but that's not allowed because we have already used 1 in the thousands place. So this cannot be 9 if there's no carrying. But if there is a carrying, what could be in this place? Then we have 9 plus 2 plus the carrying 1. That will give us 12. That would be 2 for this place. So 2 is already used again. So this cannot be 2 either. So we just discussed both cases we saw without carrying from the hundreds place. That means that in both cases 9 will not work. So now that helps us eliminate 9. Okay, so this cannot be 9. But A is already used here. So A is also immediately eliminated. That really worked because our first step is to find a small group of choices 7, 8, 9 for this box. And now we eliminated both 9 and A. So now we are confident this must be 7. Okay. What does that suggest for the rest of the boxes? Well, since 2 plus 7 is 9, 9 by itself cannot generate carrying. So the only way to generate the thousands place 1 is that there is a carrying from the hundreds place. And because of that, this digit must be 0. All right, that's wonderful. So with very solid reasoning, we have solved 2 more boxes. And at the same time, we can cross them out. There you go. Okay, now we have only 4 boxes to work on. And this is really just you have to exercise the basic technique, trial and errors. Because now it doesn't have that many possibilities for the remaining 4 boxes. You only have 3, 5, 6, and 9, and you do have 4 boxes. So you can easily try each one of them. So if this is 3, obviously you get a 7 because unit digit is always the easiest to start, all other things being equal, because you don't have to consider potential carrying from a previous digit. You are already at the unit digit. So we start at this point. 3 cannot work because that will give us 7, and 7 is already used. So this cannot be 3. How about 5? 5, it gives us 9. That potentially can work. So why don't we circle this as a potential candidate for this? So if this is a 5, 5 is 9, that's available. 6 won't work because 4 plus 6 will be 0, and 0 is here, so 6 won't work. And how about this is 9 itself? If this is 9, 4 plus 9, that's indeed 13, and 3 is available. So we circle this as another group of potential candidates for the unit digits. So with those 4 digits, 3, 5, 6, 9, we see that we only have 2 potential choices. Either it's 5, then get a 9, or it's a 9, get a 3. So that allows us to just take a brute force approach to try which one can actually work. So we consider the first choice. If this is 5 and 9, there's no carrying. 4 plus 5 equal to 9. And now we only have, we temporarily mark rows as unavailable. We only have 3 and 6 available for those 2 boxes in the 10th place. But it doesn't take long to see that cannot work. Because if you add 3 to 8, that will give you 11. And that place is not possible for 6, so this won't work. On the other hand, if you add 6 to 8, remember now we assume 5 and 9 were taken by the unit place digit, so only 3 and 6 can be tried for this tens place value. And 6 plus 8, that's 14, but 4 is here. So if we have 5 and 9 in the unit place, that won't work. So it looks like the only way to make this work would be put a 9 here and 3 here. We actually have exhausted all of choices. This must be the solution just by eliminating all other possible choices. But we still want to verify whether this is indeed the case to check whether this will work with the tens place value. So now 3 and 9, they are gone. So for tens place, we only have 5 and 6. But remember, there's a carry now. 4 plus 9, we got a 13. So there's a carry here. And now you can see that this will actually work because if put a 6 here, 6 plus 8, that's 14. 14 plus the carry from the unit place, that's 15. Indeed, we can put 5 here. And not only that, 6 plus 8, 14, 15, it does generate the carrying 1 that we actually expect to have. Okay, so the solution is 764 plus 289 equals to 1053. From this problem, you can see that this is a solidly reasoned out solution. This is no random just try and error, and really just with some luck you magically found the solution. No, it's not like that. We gave it a very solid reasoning. That's how you generally want to solve puzzle problems. You want to start with some easiest starting point, then try to crack the problem open piece by piece, because once you have a crack there, you can expand it, get additional things worked out that will lead you to further easier to work out just a point. So low-hanging fruits can lead to additional low-hanging fruits. Okay, so I know I gave you a solution, but with this problem, really just want to demonstrate how to do logical reasoning. Okay, so for this week, there's another problem that needs you to exercise very solid logical reasoning. Okay, this I guess is from this past Wednesday. So in this problem, we have two boys, Aaron and Albert. They play a game of so-called picking sticks. So what do you have in this game is that you have two piles of sticks. And in this specific problem, you have one pile having 7 sticks and the other 15 sticks. So the rules of the game are that the two players, they have taken turns to pick some sticks from one of the two piles. So the constraint is that you have to pick one or more sticks. That means that you cannot do nothing. You cannot pick 0 sticks. So every time you need to pick at least one, let's say some sticks, but from exactly one of the two piles. You cannot say, I take one from this pile and take another one from that pile. No, you only take sticks from one of the two piles, but you cannot pick 0. You have to pick at least one. That's the a rule. And how do we know who will win? The last person who can pick sticks to empty the piles, meaning that this person will pick some sticks, then nothing left. If that's the case, this person will win. So the question is that can the first person starting the game, or the second person who can win by setting up a a winning strategy. Meaning that if you go first, do you have an advantage that you can set up a strategy that guarantees you to have a win? Or no matter what you try, the second player will actually have a strategy to win in this case. Okay, there's a follow-up question. If you do find such a strategy, is such strategy unique? That is mathematically interesting because you really want to try to do some very solid reasoning here. Okay, so we want to see whether you can set up a strategy. This problem like open question. We don't know what they do, but we want to figure out a way to win. Where can we start? Well, because you need to find out strategy to win, so you do your best. You consider first, what does a win mean here? Well, the problem is that the last person who can empty the piles, meaning that the last person who can pick some sticks and nothing left, that person will win. So if that's the case, why don't we just reason backwards? We back to the very end of the game. Let's just say at this point we don't know who will win because that's what we are supposed to figure out, whether it's the first player or the second player who starts the game. Let's just consider what will happen at the very end. Someone win. At that time, the two piles will be completely empty, right? Let's consider that's backward counting. We count backwards. That start at, let's say, that's 0. Nothing left. Okay, so that means that if we go one step back at 1, now we are counting backwards. Okay, the empty state is 0. So back to 1, that means the very last step, the last person, what will this guy have in order to win? In this case, because after this guy's pick, we have nothing left. So this guy must face the case where you do have one pile that has some sticks and the other pile is empty. It doesn't matter which pile, but we do know what this guy must face in this at this point is that exactly one pile is empty. The other pile does have sticks. It doesn't matter how many sticks because this guy can take any sticks as long as it's more than at least 1, more than 0. So for example, if this is 2, 0, this guy will pick up everything from this pile. So that means that at this point, if this guy indeed win, so when he last pick, he will face this situation exactly. Nothing else can give him a win. What do we mean by nothing else? If the other pile also has some sticks, because the rule says that you can only pick from one pile, then he cannot win because he cannot empty both at the same time. So indeed, when this guy start at last round, he will have to face one empty pile and the other non-empty. It doesn't matter how many that the non-empty pile has. Okay, if now we understand this situation, how about the guy played before him? So that would be count backwards number 2. Because if the number 1 situation, one empty, one non-empty is a situation, then you can see that this guy at this stage, he definitely want to avoid a situation as we see at this one stage, because that way this guy will lose, right? So it's not that he is not smart, create a situation for the other guy to win. He created a situation only because he had to. He had no choice but to, because he still needs to play, and by the rules, the only way for this to happen at this stage one is that at stage two, the other losing guy will have a case where he has to pick one of the piles to empty that pile. Because whenever he has a choice, he wants to avoid this situation. He did not want this to happen, having one pile empty for the other guy to win. So that means that when this guy is picking, he must face a situation. Both piles are non-empty, and not just that, both piles must have exactly one stick. Think about it. Exactly one stick. Only in such a case, because this guy must pick at least one pick, so he will have to pick one and empty that particular pile, and that will create a situation for the winning player in the next pick to pick the other one stick. Think about it. Anything other than this situation, you will not generate, or in other words, this stage two player can avoid such a situation because both piles need to be non-empty. If one is empty, this guy will be in the situation as the next winning guy. He will win, but by cleaning up the only non-empty. So both piles need to be non-empty. If there is this one pile having more than one stick, this guy can avoid this situation because he will continue to pick one stick from that pile which has more than one stick, right? He can avoid the situation that he must, at this point, empty one of the two piles and creating a winning situation for the next player. So that means that at this stage two, the two piles must be like this exactly. Each pile has exactly one stick. Okay, that's a significant and very interesting discovery. So that gives us further um, reasoning, uh, just foundation to the next round. We go backward one more time. Remember, this is now the winning player's pick because we know this guy went. So now remember, this is the winning player's round. What did this guy do to force such a situation for the losing guy? Namely, has a 1-1 piles. That means that in the previous round, because he only picked from one of the two piles, at that time, at least one of the two piles already had one stick because he cannot pick from both. So must be case that one of them at that point had exactly one stick. But how about the other one? Well, clearly, because that's the case, this winning player did not pick that remaining one. Because that, if he did, he would be silly allowing the other player to win. So he must have picked some sticks from the other pile. So we know the other pile had more than one. It actually doesn't matter how many sticks there, could be two or three, because whatever number there, this guy, the winning guy, will pick most of them and only leave one stick left to force a losing situation for the losing player in this round. Remember, this is a losing situation because you have 1-1, you have no choice but just picking one. So that means that at this stage 3, the winning player will face a situation where he had exactly one pile which had one stick, and the other pile had more than one stick. It doesn't really matter how many more. At least it's two. That will do it. So this winning player will pick all but one sticks from this pile to force a situation 1-1 for the losing guy to lose. Okay, if that's the situation, then we can go back one more step, and this will essentially conclude our reasoning and enable us to find the pattern. What this guy faced, the losing guy faced in this round, that he had to create a situation like one and more for the winning guy. We can see that the only situation for this case is 2-2. Remember, after this guy's pick, we have one and more, say 1 and 3, 1 and 4. But the losing guy definitely want to avoid such a situation in the first place. But he had no choice to create this situation 1 and more. Why? Because only because he actually faced a situation must be 2-2. Why? The reason is that if this is not 2-2, say anything, one has at least 2 and the other has say 3 or 4, whatever, the losing guy did not have to create such a situation. Because that's just a 2-3. He can actually pick one from the 3 to leave a 2-2 situation for the winning guy. And that in that case, the winning guy actually will lose because we know this is one and more situation. If you have 2-2, that doesn't match this one more situation. So the only reason the losing guy had to leave a one more situation to the winning guy is because he has a 2-2 situation. And he has no choice but to pick at least one from them. He doesn't want to pick 2 from either because that he will immediately lose because he emptied one pile. The other player can immediately empty the other pile. He still wants to struggle a little bit. So if it's a 2-2, he can only pick one of them and leave a 1-2 situation. Remember, this doesn't have to be 1-3, just one more. So if this is a 2-2, then this losing player at this round will have no choice but to create this one more situation for the winning player. Anything else, he can avoid such a losing situation. So that really gives us the clue. You see that what happened with the losing guy situation. Every time he faced a situation that both piles have exactly the same numbers. And that if that happened, he has to pick at least some sticks. It doesn't matter now from which pile because both piles have exactly the same number. So he picked some numbers, and the winning player in the next round can immediately match and picking exactly the same numbers of sticks from the other pile, recreating a balanced situation for the losing guy. So the losing guy next time will once again facing exactly the same numbers in both piles. So now you can see that the reasoning lead us to make a hypothesis. We propose that whenever a guy facing a situation where both piles have exactly the same number of sticks, then this guy is in a losing situation. And we just argued why. Okay? So if that's the case, we will see that from the very beginning we have 7 here and 15 here. And if you are the first player, what will you do? Apparently, you won't just create the situation we just described for the other player to lose. So you will take 8 sticks away from this pile to create a 7-7 situation for the losing guy. We explain why that guy will lose, because whenever this situation is in place, he cannot do anything. The two piles have exactly the same number of sticks, and he has to pick from one of them. And after his pick, the two piles become unbalanced. And the other player, which means the winning player, will rebalance the piles again by taking exactly the same sticks that the losing players just took from the other pile that have more remaining sticks. So, for example, in this 7-7 situation, the losing guy, the second player, has no choice. It doesn't matter how many sticks he picks. 1, 2, 3. Say, let's say he picks 3 from this place, it becomes 4. So the winning player come back, seeing there are 4 here, there are 7 here. He will also just do exactly what the losing player just did. He also takes 3 away, remaking the two piles balanced. So next time the losing player come back facing exactly the same situation, 4-4, all he can do is just to take some additional more. So you will see that from the very beginning, after you have a 7-7 situation, all the losing player can do is just keep this decreasing, and all the winning player had to do is just force every time create a balanced situation for the losing guy. Could be go down like 6-6 or direct faster 3-3, but at the end of the day, it will go to 1-1. And in that case, the losing player now has been really cornered. Facing 1-1, he has no choice. Just pick one from them, and then the winning player come back, empty the both piles. So this is the strategy we just spelled out, but we did not just find this strategy by random guess. It just solid reason, and this reasoning is from backward reasoning. We start from very end. At step 0, you have 2 empty piles. What happened? Well, in that case, the winning player must face one empty and the other not empty. In that case, he can win. And this step is quite critical, give us a lot of just insight into the nature of this game. That is that the losing player, every time he will face a situation, he had exactly the same number of sticks in both piles. He cannot make a choice. So that also leaves the other player a winning strategy in the next step. So now we have to answer an interesting question. Is such a strategy unique? Well, we just figured out such a strategy, right? So for the first player, you have 7-15. You take A from the 15 stick pile to create a 7-7 situation. But we know this is a winning strategy. Is this strategy unique? It means that is there any other winning strategy in this game? Well, the answer is no. Why? Well, we can use actually one of the greatest technique in mathematics. We call that contradiction. Oops. Sorry, I should not clean up everything here. Ooh. Yeah. Okay, that's fine. So let's just consider what happened if you have any other winning strategy. Initially, we have 7 and 5. Let's assume you have another strategy that guarantees you win, and that's different from our strategy. Meaning that at any step, the winning player can have another strategy that is unbalanced. So whatever that strategy is, after this first step, if this guy, the presumed winner take any stakes that is not 7-7, what happened? He left the door wide open for the other player to win, right? Let's just say he takes a 5 from this 15, he creates a 7-10 situation. Or, silly enough, take a 2 from the 7, create a 5-15 situation. Either way, in either case, whenever he leave the two piles unbalanced, because we already just proved the balancing strategy is a winning strategy. Whenever he left the two piles unbalanced, the other presumed losing player will come back, take advantage of his mistake. He will make those two piles balanced. And once he did that, the winner can never reverse his mistake, because now the other guy get the upper hand, creating a balanced situation for him. He will become the loser, right? So this is a very straightforward reasoning. This strategy is actually unique. Anything different from this will guarantee a lose, because the other guy will take advantage. Instead, the guy will employ what we just did, make this a losing situation for the winner. So you cannot do anything else. Anything else, you will lose. So that actually just proves why this winning strategy, not only winning, but this is the only strategy that can win. Okay, so I hope that through this problem, you can actually learn quite a bit about some very important just principles in mathematical reasoning. Okay, first, you want a rigorous reasoning. Sometimes a problem solution is no strict rigorous. You need some trial and errors, but not for this problem. You can have a very solid reasoning chain. The other thing is we just discussed a little bit about this great technique called contradiction. Well, we'll learn a lot of problems later regarding this contradiction principle as a technique to prove certain things. All right, that's for this week's homework discussion. So now we will go back to our problem from last time. This is today's lecture will be really important for those of you who really want to do excellent competition math in the future. And today we will talk about mathematical induction. For those of you who have already heard of this, don't go away, because we'll give this a very kind of thorough discussion, and that can really help you understand what mathematical induction is all about. So remember last time we have this famous summation problem, and the legend said that one of the greatest mathematician, Carl Gauss, was able to solve this when he was really young. And last time we see this is the formula for this summation, and we discussed how to generate this formula just by arithmetical method, but also we gave this formula two very different interpretation. One is geometry, which is based on how you would calculate the area of a trapezoid. So that is that we know that the formula for area of a trapezoid is a plus b, top plus base, the length, then times the height, then divided by 2. And this looks exactly the same when we have a general Gaussian summation, say from 3, 4, 5, say any number, say 29. We want to add the first number, 3, to the last number, 29, times the total number in this sequence. In this case, is 29 minus 3 plus 1, or minus 2. That's 27. so divided by 2. And 27 corresponds to this height h, which is the height of the trapezoid. And 29 corresponds to b, which is the longer base, which is this one. B and 3 correspond to A, which is this top, the shorter side, shorter base, I should say, of the trapezoid. So the formula is exactly, or at least look exactly the same. And it's only because the underlying trick is that you do this trapezoid patch. You add one more identical trapezoid to make a parallelogram. Okay, that's the geometric interpretation. We also talk about a combinatorics proof, which use two counting to get the same result. So to two different countings that you have a single round robin just game among n+1 team, so that each team will play exactly one game against another. So the total number of game of played must be 1 plus 2 plus n, assuming you have n+1 teams. So that way, this is how you would count the total number of games. But at the same time, there's another way of counting this problem. That is, each team will play exactly n games, but there are n+1 teams. So the total of games played for the whole group would be n times n+1 divided by 2. The reason we need to divide this by 2 is because in that way, each game was actually counted twice by both teams, because we are multiplying the number of teams with the number of game each team plays. That's n times n+1. But each game was counted twice, so we have to divide it by 2. That way gave us a super fast formula. We just merely by making arguments about counting, you get this point. That's called bijective proof, okay, in mathematics. So today we'll look at this problem at a very different angle. We don't know anything about this. We don't know geometry, we don't know combinatorics or counting. We just look at this formula. How do we prove this directly? Well, we don't use techniques like combining 1 with n, 2 with n+1, and count how many pairs we have, or using anything like making an exactly copy. We just look at this formula itself to think about a very straightforward way of counting this, or adding this, I should say. And you might think that at this point, is this really true? If it is true, what happened to verify the next one? So we have 1 plus 2 plus 3 plus n plus last one equals to n times n+1 divided by 2. If this is true, does this guarantee that this will be true for all the numbers, all the natural numbers m? Because if this version is true, we only test the first n, right? We plus 1 plus 2 up to this number m. But how about the next one? If we add another, the next number would be n+1, meaning that if we do know 1 plus 2 plus 3 plus n equals to n times n+1 divided by 2, we still don't know whether this will continue to be true, meaning that if we add one more, will this be also true? If this remains to be true, what would be the right-hand side look like? Remember now, we are not just adding up to n, we are adding up to n+1. If this formula continues to be true, then we have to update the right-hand side, because now what was n becomes n+1. So this formula has to be n+1 times the next number being multiplied is 1 more than the first number, so this would be n plus 2 divided by 2, right? Because the formula looks, remember, this is the very meaning of algebra. We use n to represent any number. So the formula is generally true, means that any number n should work. So also literally, we take this to be true for the first n numbers, and at this point, if n is a specific number, it's fixed. But this next one must be also true, right? How do we know this is true? Well, the thing is that if you already know this is true, in order to evaluate whether this is true, we don't have to redo everything from scratch again. We can simply use the fact that this is true because that's our initial starting point. We just think about this is true and we want to examine whether this is true. So we can simply plug this right hand side into this place, right? So essentially what we will do, we will evaluate, maybe I should use blue. We will use the earlier result, n times n plus 1 divided by 2, because we know this is exactly the same as 1 plus 2 plus up to m. We know that. Now we want to add one more, which is the next number, n plus 1. We want to ask whether this is true, plus 1. This is just our intuitive thinking about the nature of this problem. Is this true? Well, at this point, we only actually have two numbers on the left-hand side. We can actually manipulate this, okay? So this will be actually shown later. This is indeed true. But before doing that, let's think about a larger class of problem of this type of nature. Remember, in the class, we talk about the very meaning of natural numbers. We go back to that basic definition to see what happened when we define natural numbers through a counting process. Essentially, we use a very important increment function. But remember, we not only need that increment function, we also need to make assumption about the initial starting point, which is 0, right? Why did we define natural numbers in this way? We first assume there's an initial state for the counting, and which gives us the all-important concept of 0. That number is 0. And now with the increment function, what we did in defining the natural number is that we define 1 as an increment from 0. It only needs two things. One is 0 itself, one is the increment operation, which will apply on 0. So 1 is increment 0. But from that point on, we will be able to get 2 because 2 is defined as an increment from 1. And the rest is straightforward continuation. We keep doing it. So 3 will be defined as an increment on 2. So what is going on here? It's a recursive definition. And this recursive definition is very important because you only need two things. One is a starting point. One is a mechanism to take one step. But that step allows you to take a further step once you get the result of that first step, which is from 0 to 1. Once you have 1, you will do exactly the same increment to get 2. So this is a recursive definition. But this fundamental idea that you can go from a very small set of conditions, namely you have an initial state and some action. Once you have done that, that same action can allow you to go one step further, and then another step further, and another step further, without ever stopping. So that's exactly the principle, the idea behind mathematical induction. And in fact, we will show later today our very definition of addition will also based on this idea. But let's review what we have for this principle. Okay, so this is a very formal introduction of the principle as mathematical induction, and we will explain this is actually one of the missing axioms in our set of axioms to define the natural numbers. Okay, what is the principle of mathematical induction? Well, it's about natural numbers. Natural numbers, now we know we have defined them as from 0 and 1, 2, 3. We start from 0. So, in general, this is actually not just an axiom, but a kind of a template for creating a lot of axioms. So, it's technically called an axiom schema, but we don't have to worry about those just kind of arcane, strange names. We just see what it is about. This is quite abstract, so stay with me, be very slow about what is going on, okay? Let's just say we have a property. So this is truly in the abstract. We don't describe what exactly this property is because it's actually a template. So let's just say we have a property that belongs to a natural number n, okay? We want to test whether this property is true for all the numbers, all the natural numbers n, at least starting at some point. That means that because we have infinitely many natural numbers, if this property is true from the very first natural number, meaning from 0, it's true for 0 and 1, 2, that's great. But we allow ourselves sometimes a little bit of flexibility, saying we don't care about 3, the first 3, as long as starting from 4, from that point on, this property is true for all the natural numbers. We'll be happy with that as well. Meaning that we can forgive the first 3, we only care starting from 4. So from 4, 5, 6, 7, 8, this property is always true. That will do it. So that's why it came with the following just definitions. Let's just say this property about pk is true. K is called the initial state or initial number. All we need to know is that k is actually a natural number. That means that greater than or equal to 0. K could be 1, could be 2, but k generally can be 0. So let's just suppose at this initial number, natural number k, this property is true. Remember, k is just our initial natural number. It can be 0, but sometimes it can be 1 or even greater than 1, 2, 3. Doesn't matter. As long as this pk is true for this very first natural number, then this is a hypothesis. If this is true, now we need a second hypothesis, which is all important, super critical for this principle. Let's just assume this property Pn is true. N is a natural number equal to or greater than k. It cannot go before k. So, but we assume whenever this property is actually true for this natural number n, it will always be true for the next natural numbers for this property to be true. Read this statement very slowly and carefully. Suppose that whenever, this is also important, every word in this statement is critical, okay? Whenever this statement, this property P is true for natural number n, where n has these, has to be at least k, our initial one. It cannot go before the initial one. But any number after the initial for n, whenever this Pn is true, then we know the next one is also true, meaning that n plus 1, for the next natural numbers, this property is also true. Read this statement one more time. Whenever Pn is true, Pn plus 1 is also true. We have two hypotheses. If they're both correct, if they're both true, then we have a conclusion, and that comes in number 3 here. Then we argue that this property is true for every natural number starting at k. K, remember, once again, is our initial. So whenever this is true, number 1, number 2, they are true, then we argue Pn is actually true for all the natural numbers starting at k. K plus 1, k plus 2, go to infinity. Why it looks this is actually the case for anything? It's just by our argument, right? If we have a starting point at k, that's 1. And if 2 is also true, remember 2 says that whenever Pn is true, the next one will be true. Then we start at k. Because of 2, we know pk plus 1 is true. For the next number is true. But this same argument can be applied again regarding k plus 1. Because we know property is true for k plus 1. By reapplying this number 2 hypothesis, we know the same property must be true for k plus 2, the next one, right? And once again, at that point, we can argue again by this number 2. This property must be true for k plus 3. And you can see that this argument will never stop. Therefore, we can see why we can argue that Pn is always true for any natural number n is at least k. We just argue that because of this process, it will goes on forever. Therefore, this property P will be always true for any natural number that is at least k. So what is exactly we put down here? This principle of mathematical induction. We assume this is general truth. Whenever you can make an argument like this, number 3 will be always true. We just assume this whole reasoning process itself is legit. It's totally good. Therefore, we take this very induction process as true, as an axiom. In other words, this whole process is assumed to be true without any proof. Whenever we can find anything, a pattern that can be attached to this argument, then we will be able to argue that this property is generally true for all the natural numbers. Look, this looks super abstract, for young students like you. You have to read this multiple times and think about it very deeply. Now you may ask this question: what is that property? What do we mean by that property? That's a very good question because we haven't specified what exactly that property is. But that just a property is generally something related to this natural number n. And now we have our first example right here. What is this property? With this number, natural number n, that property is this formula. That's what we are going to prove next. We want to prove by mathematical induction this general formula is true times n plus 1 divided by 2. This very formula itself is the property we just talked about. Does that make sense? This is something, and this is related to n, to the number n. On the left-hand side of the equation or the inequality of equality, we have something related to n, right? It's 1 plus 2 plus 3 plus all the way to n. And that's also the case for the right-hand side. What is right-hand side? It's a specific multiplication number divided by 2. It's also related to n. So this whole thing, this equality, is the property we just talked about. Okay, so now the question is that, is this generally true? Yes, we know it's true because last time we had at least 3 ways to show this is true, right? Now today we are going to show by a fourth way and by mathematical induction. So that's just your teacher gives you this problem. Prove this is true. So cross out the question mark. You want to show this is true. Now we want to show you this is indeed true by mathematical induction. Okay? So, how do we do this? Just follow the step that was outlined in this on this slide. Pn, a property pertaining to a natural number n. In this specific case, it's this formula. We want to show this property is true for any natural number n greater than or equal to 1. Okay? So in this case, we have to verify whether the first hypothesis, number 1 here, is true. Well, in general, because this is so general, k can start at 0, the very first natural number in our definition. But in this formula, we see that n needs to be at least 1. That's the very first one, right? Because we don't want to go back to 0. There's no 0 here. So let's just verify the initial step if when n equal to 1, whether this is true. So our initial, the first step is when n equals to 1, the left-hand side of the formula is just 1 plus, up to 1. So left-hand side is just 1 itself. There's no further addition because that's the very last one. So there's no real addition. So 1 equals to what happened to the right-hand side? N equals to 1. 1 times 1 plus 1. Remember, n is 1 for now, divided by 2. This is indeed the case. 1 times 2 divided by 2. That's just 1. So this is indeed the case. This is true. So we just finished the first big deal. That is that this hypothesis is actually correct. Okay? So we just show that this is actually true. Now, the next step is our hypothesis step. Induction step. Sorry. The second step is that we want to show when n equals to some natural number, general natural number, number that is at least k greater than or equal to 1. So we assume this is true, right? We want to show Pn is true. This is the hypothesis in this one. Assume this is true. So that means that 1 plus 2 plus up to k equals to k times k plus 1 divided by 2. Okay? This is how you carry out the mathematical induction. You assume when n equals to k, some k, this is generally true. But you need to prove the second part in this number 2. That is Pn plus 1 is also true. So now we need to show 1 plus 2 plus k plus 1. We want to show when k is k plus 1, this will be equal to, and for now we don't know, so we put a question mark. When k becomes k plus 1, how should we update the right hand side? It would be k plus 1 times k plus 2. Remember now k becomes k plus 1. So correspondingly, for each of rows, we have to increment by 1. So the right hand side has to be k plus 1 times k plus 2 divided by 2. We don't know whether this is true, and that's what we need to prove. If this is indeed true, then what did we do? We finished the second, this hypothesis thing, right? Suppose that whenever Pn is true, then Pn plus 1 is true. So we suppose that when m equals to k, this is true. We assume this is true. Now we need to prove when n equals to k plus 1, whether this is again true. That's the thing we need to figure out. Remember, this is an unproven statement yet, and that's what we are going to do. So what we are going to do, in general, the very reason for induction is that we can take advantage of the hypothesis for when n equals to k, so we can take advantage of this part. So the left-hand side is nothing but 1 plus 2 plus up to k. We group them together, then plus k plus 1, right? This is the left-hand side. We are adding those two parts together. But what is this? By our hypothesis, this just equals to k times k plus 1 divided by 2. Remember, this is based on our hypothesis in this induction step. That is exactly what we say. Suppose that whenever Pn is true, so Pn is true is assumed in this step, and that is really critical. If this is true, then we will see what happened. And what is this? You can see clearly in both terms, we have a k plus 1 here. By using the distributive property, we can factor out. For those of you who have not known distributive property, you'll recognize that something like, say, 6 plus 8, you can factor out because both are even numbers. We can factor out the 2 because 6 is equals to 2 times 3 and 8 is 2 times 4. So we can factor out 2, so this will be equal to 3 plus 4. And obviously, this is equal to 2 times 7, right? And 6 plus 8 is exactly 14. That's 2 times 7. And this is called distributive property by factoring out is 2. So when we do this, we can factor out k plus 1 from both terms. And for the first one, it will become, because this guy is now being factored out, this will be k over 2 divided by 2 plus 1. Okay, and what is this? This is exactly k plus 1 times 2 over k plus 2. Remember, 1 is just 2 over 2, right? You have already learned some basic fraction from your K to 4. And what is this? If we put 2 out, this is exactly what we want here. Compare this. Did you see that? This is exactly what we want to prove. Is this true? Yes. We just showed that this is indeed true. So no longer a question mark here, but a big green check mark. This is indeed true. So what did we do? We just show that if n equals to k, this formula, this summation formula is true, then for the next k, k plus 1, this formula must be also true. Okay, this is called mathematical induction. And because this is an axiom, we agreed whenever we can do this, if we can verify first one, initial state is true, and we can also verify the induction step, that is that whenever Pn is true, if we can show Pn plus 1 is also true, with those two steps combined together, we will be able to argue Pn is true for all the natural numbers starting at this initial one at k. Because this is an axiom, we just show this formula, the Gauss summation, is generally true for every natural number starting at 1. Okay, this is a super important stuff if you want to do serious math. Mathematical induction is such a fundamental principle that will be used just in many, many problems. If you get most of what we just talked about, great. As a 5th grader, you are way ahead of most of the students in the 8th grade. They do not know anything about this in this country. Most of 8th graders never heard of this, let me tell you. But if you still have something that kind of just unconvinced, read this very carefully. Think about it. What is exactly about mathematical induction? You want to go back to our example, like how we define the natural numbers. It's the same idea. You have an initial state, you have a mechanism that allows you to go one step further, but that mechanism can be repeated without any just limitation, go into infinity about these natural numbers. Okay, and this is the mathematical induction principle. All right, very important. But now let's spend 10 minutes to talk about another application. Okay, so in our lecture we talk about natural numbers, right? Remember, our natural numbers defined through this counting process right here. But before formally defining natural numbers, we also talk about 4 axioms. If you recall, what are those 4 axioms? The first one is like just we said, we all have to agree 0 is a natural number. That's essentially the initial state of our counting process. We always count from 1, but starting from 0. So we need this as an axiom. And the next axiom is there exists an increment operation. That's once again super important. That gives us the very first step from 0 to 1, which is a huge deal. From 0 to 1 is the milestone. It's a breakthrough. From that point on from 1 to 2, from 2 to 3, they are essentially all the same thing. So two things super important. You have 0, you have a from 0 to 1 step, which is this increment function. So we have the second axiom. And we explain we need some additional guard to make sure that there's no looping back or any looping at all. So we need two additional axioms say no natural number can have 0 as its next in counting number. You can never count back, say from 5 back to 0 in this counting process. We also need to make sure that 1, 2, 3, 4, 5, you cannot say the next one is 3. That's where the number 4 axiom we need. This essentially say all the different natural numbers will have different next in counting natural numbers. So this counting process will only go forward 1, 2, 3, 4 all the way to infinity. It will never go back, say 1, 2, 3, 4, 5, 3, back to 3. That's not allowed. That's what this axiom does. So far we gave you 4 axioms. Okay, what we are studying is a very advanced higher math concept using the so-called piano axiom to axiomatize the natural numbers. However, we deliberately left out one important axiom. And what is that axiom? It's exactly the mathematical induction axiom. This is actually a group of axioms. We leave this out because this is too advanced for regular 5th grade students. If we introduce this concept, this will become college math. It's just too advanced. However, because we are doing enrichment here, we will introduce this to you early on because mathematical induction is so important. It will have many applications in future enrichment classes, and you really just need to get an initial grapple on it. You don't have to understand it completely, but it will come naturally when you see more and more such examples. And today we will actually show you one example of this. All right? And that's something called commutative law of addition over natural numbers. We already gave you some homework to get started on this concept. This is so important. And today we are going to use mathematical induction to prove it. In free Asian math, because we did not add this mathematical induction as an axiom, look, we are only talking about this in this enrichment program, right? So for students who would not want to learn more additional math, not taking this enrichment program, we will never talk this to them. They will not assume the availability of mathematical induction. As the result, this commutative law, which looks so simple, so natural, will never be proven for them. We have to assume this commutative law is an axiom, is something that does not need a proof. We take it as a truth without further proof. That's because, exactly because, we did not assume this mathematical induction principle. But in this enrichment program now, we have this mathematical induction available. So now we will be able to say this addition is commutative can be actually proven. Okay, and then we will give a easy proof. What is the commutative law? You have two natural numbers, m and n. Let's just say 3 and 5. You know, you're in 5th grade, you know 3 plus 5 equals to 5 plus 3. But why that is generally true? This looks very trivial, very simple, right? But to show this is true is not easy, okay? It's very intuitive. It's very obvious. You cannot think about otherwise. This cannot be true. This is not true. That's impossible, right? You have lot of ways to intuitively understand why this is the case. For example, in the AR's video, Richard used the example. If you have watched that video, he used example of wearing hats. He has some hats in one hand, some other hats in the other hand. Excuse me, count how many hats he have, and swap them with both hands. Still the same set of hats, so the number must be the same. That's not a proof. At least that's not a rigorous proof. Okay? That's just an intuitive proof. It's not mathematically rigorous. However, we can start somewhere else, and that somewhere else is the mathematical induction. If we assume that mathematical induction principle is true, if we assume that's an axiom, then we will be able to prove m plus n equals to m plus m. And that's what we are going to do next. Okay? Excuse me. So, we want to prove m plus n equals to m plus n, where mn are natural numbers. Okay? So, how do we prove this with mathematical induction? Remember, in any mathematical induction, we start with the initial step. So, because m and n are any natural numbers, we actually don't need to do anything with m. The first one being add on. We just need to show for all the natural numbers from 0, 2, 2, 3, all the way anything. If this is true for any n, we will be finished, right? So you can naturally see there's a structure here that involves n has to be 0, 1, 2, 3, any natural numbers. So we will perform this mathematical induction based on the second natural number n. So we first check whether this is true for n equals to 0, right? Remember, we have an initial point, and that initial point can be any natural number, but it can go to the very first one, which is 0 here. We want to check whether m plus 0 equals to 0 plus m. Okay? Is this true? This is our question mark. Is this true? Well, we have to go back to the very definition of addition, right? If you don't recall, how do we define addition? This is we just learned this, right? Addition of natural numbers. And this is the addition. So by this definition, what is our m plus 0? M plus 0 equals to m. That's by definition. If you don't remember this, this is by definition. M plus 0 is performing no plus 1, so that must be 0, m itself. So we essentially define m plus 0 equals to m. But is that also g plus m? Is this true? Well, we have to go to definition again. What is 0 plus m? Well, 0 plus m is simply from 0, it do n times of counting, right? By this definition, 0 plus n is performing the counting increment n times. So therefore, in this case, 0 plus m is once again equals to m. This is once again by definition our addition. So therefore, we just finished the proof. Very trivial, both by definition. This is indeed m plus 0 equals to 0 plus m, satisfying the commutative law for the initial stage when n equals to 0. So check. We have finished the first initial step for performing mathematical induction on this. Remember, once again, we are trying to do the induction on this second number n. We want to show for any natural number this is true. So first step that when n equals to 0. Now the next step, assume when n equals to k, where k is any natural number, we have m plus k. Well, we should write to this equals to m plus k equals to k plus m, right? So this is an assumption. The commutative law works for when n equals to k. What we need to do to finish the induction step, we need to show m plus k plus 1 equals to k plus 1 plus m. Okay, right? So by the commutative law, we will have to write something like this. Okay? How do we do that? Well, we will have to show what is this by definition. We already know m plus k plus 1 is, by definition, is go from m, you plus 1 plus 1 plus 1 plus 1 k times, right? This is the very definition, k times. So if we add one more, it just becomes k plus 1 times. So essentially k times, then one more time, and one more time. Okay? Right? This is the very definition of m plus k plus 1. That's our definition. But by our definition, this is already this one. At this point, this is m plus k plus 1, right? So what this means is that m plus k plus 1 equals to m plus k plus 1, right? Agree? But by our induction assumption here, we know m plus k equals to k plus m. So by this assumption in our induction step, we know this one equals to this one. So this equals to k plus m plus 1. Right? This equals to k plus m plus 1. You all agree? This looks trivial, but this is significant because we are taking advantage of the hypothesis in this induction step. But what is k plus m? Well, k plus m, by our very definition of addition, remember we have still go back to the definition of k plus m, is nothing but k started at k plus 1 plus 1 plus 1 plus 1 m times This is what k plus m all about. And then we have one more plus 1. So this is plus 1. So essentially we start at the k, perform m times addition, then plus 1 more addition. Okay? Now you can see that this is just straightforward counting not just m times, but also counting 1 more times. So it's from k counting m plus 1 times. So therefore, we can easily see that this is essentially counting. You can regroup this into we count 1 time first, then count m times. Right? Because essentially you counting that many times. It doesn't really matter you put counting m times first or counting 1 time first. In total, that's the total number of counting you have performed. So this is nothing but k plus 1 plus m. Now take a look at what we have. We start with our next step, updating k to k plus 1 through a series of seemingly quite trivial manipulation, but each step is important. We arrive at this thing, which is exactly what we need to prove the commutative law for the step when n equals to k plus 1. Look at what we did. We finished the first initial check when n equals to 0. The commutative law works. M plus 0 equals to 0 plus m. Then we assume when n equals to k, this is also true. M plus k equals to k plus m. Remember, this time is hypothesis. We assume this is true, but we need this to show if this is true, then m plus k plus 1 equals to k plus 1 plus m. Therefore, we complete the induction step. When we update k into k plus 1, we once again prove the commutative law works for the next number of k plus 1. Now, we essentially have finished both steps in this mathematical induction, the first one and the second one. Therefore, based on this principle as mathematical induction, we can conclude now Pn, this property, is true for every natural numbers. And what is the property we are talking about here? The property is just the commutative law that we want to prove. So this is the law that we want to prove. And here, the property is on the second number n. So we just prove m plus n equals to m plus m for any natural number n. But at the same time, the starting point m, Mary, is also x, any natural numbers. Therefore, we just prove for any natural numbers m and n, m plus n equals to m plus m. And we finish the proof of the commutative law. Don't assume this is very trivial, because if we cannot do mathematical induction, this won't be able to be proven. Okay? So very significant assumption, and that's actually our missing fifth axiom for the Peano axiom system. But in free Asian math, we do not assume this mathematical induction axiom for fifth graders. Therefore, if we go back to regular lectures for free Asian math, you will see next week this commutative law is assumed to be true. In other words, it's assumed to be axiom, not a proven theorem. What we just did, we proved this proposition as a theorem, which is a big difference. Okay? So, I hope you have truly at least get the intuitive understanding of how mathematical induction works. Super important. Have a lot of fun. All right, I will see you next week on Wednesday. Bye.